For this one, we're going to start with the tangent line problem. So you wouldn't think this would be a problem, but the tangent line problem derived from when you had a tangent line to something like a curve. So tangent line, first of all, is something that touches at, at one point here, which is easy when you think about on maybe a geometric figure. But when you start talking about a curve and you're like, well, what is the tangent line doing here? Then you start to notice that there's many places on this curve that you could have a tangent line. And where on the tangent line directly affects what's happening. I mean, where on the curve directly affects what's happening with the tangent line. So if you look at this guy right here, this tangent line's horizontal. But if we go down in another piece, like say we went to a piece that curves down, that tangent line has a negative slope, but on the other side, the tangent line would have a positive slope. And so you can't just say what's the slope of the tangent line to this curve, because then you have to be more specific. You're like, where on the curve? Where are you talking about? Because that tangent line is constantly changing. And so that is where they actually developed what we start to know as derivative, all right? And they give you the second page over there. They give you the actual definition of tangent line with a slope m, and they show you how they derive it. So they say, well, the problem with finding the slope of this line is that I only have one point that I'm referencing. And way back from like Algebra 1 geometry days that to find the slope of the line, you need 2 points. That's the whole goal, because you have to do rise over run, change of y over change of x. And so they actually started using a secant line. Secant line has 2 points of intersection. And they said, well, let's see, they start here. Well, let's just take these 2 points and we'll estimate the slope of the tangent line to be this. And so that's easy. We just do y2 minus y1 over x2 minus x1, and I can give you that slope. And they said, well, let's make it a little bit closer. So let's actually make these change. So, change in y and change in x, right? Let's make those a little bit smaller and a little bit smaller and a little bit smaller. And then you actually have the tangent line. And so that's what they did. They took the secant line and they actually made the difference between the 2 points small enough that it was actually the slope of the tangent line. And that's where they get this long definition of slope of the tangent line. All right? They said, well, we know slope is change in y over change in x. Easy enough, all right? What we want to do is we want to make that change in x nothing. But what happens when we make it nothing? We have a denominator issue, right? So technically they're saying, okay, the function at c plus delta x, that's your y value, y2, minus the function at c, that's y1, over change in x. This is your slope function. This is your slope definition. This is exactly what you would write for slope. You would just write it like this. They just want the difference here to be nothing. Well, then you run into a problem, except that limit does not matter if you are undefined. It actually just matters what's happening all the way up to that point. So it's okay if it's undefined at that point. It's okay if it's undefined at 0. They strictly want to know what's happening as you approach 0, as you approach it. And so they will use this long definition as slope of the tangent line. So let's first look and see how it's used. How is this used? How does this help us? So look at the first example there on page 96. Find the slope of the graph, and they've given us f of x equals 2x minus 3 at the point 2, 1. Okay, at the point 2, 1 specifically. And so we are going to use that long definition. We're going to say our c that we have is my x value, 2. My c value is my 2. And so we're going to use that long definition that they gave us, f of c plus delta x minus f of c all over delta x. All right? So that's what we're going to do. We're going to plug that in. All right. And so we are going to use c plus delta x as what I plug into the function first. So if I plug that in, I get 2 times c plus, well, instead of c, we're going to say 2 because we know that's what it is. 2, and my c is 2. 2 plus delta x, all right? That is my f of c plus delta x. I just plugged it in. Minus my f of 2, or f of c. Well, if I plug a 2 in, I get 2 times 2 minus 3. I'm just plugging in a 2, right? All over my delta x, all right? And this is a limit problem. So I want to know what happens as delta x approaches 0. I have a problem with that right now, but I'm going to simplify it first to see if I still have a problem, all right? And so to simplify it, you're just going to do basic algebra, order of operations. We're going to distribute my 2. So I have 4 plus 2 delta x minus, and this is 4 minus 3. All right, 4 minus 3. So minus 4 minus 3. Okay? And it looks like this. All right. So I have, oh, and I forgot. Oh, it helps to write this rest of my equation there. It helps to write that minus 3 minus 4. There we go. All right, so I have 4 minus 3, and then I have minus 4, and if I distribute this through, I'll have 4 plus 2 delta x minus 3 minus 4 plus 3, all over delta x, all right? On the top, you should see what happens. 4 minus 4, negative 3 plus 3. So I get the limit, still a limit problem, as delta x approaches 0 of 2 delta x over delta x. Yep, I can cancel my delta x's, and I get that my limit is 2.
I feel like I'm gonna write my delta, and I'm gonna think it's like 20.
So what is that telling us? This is actually telling us the slope of that function at the point 2, 1. Now, they gave us a linear function. Did they not? I mean, 2x minus 3. That is in the form mx plus b. What is the slope of that line?
2.
It's 2. So with a line, that's rather simple. The slope will always be 2. Any point we choose here, the slope is going to be 2 because the slope of the line is 2. They gave us an easy one, but it works with a curve. All right, so they gave us one that we can visually very simply see. Of course, my slope's going to be 2. At any point, it's going to be 2. If we had plugged in any point on that line, we would have gotten a slope of 2 because that is the slope of that line. So then they give us one that is a curve. And so the curve will actually change based on what happens. Now, when they give us a curve, which is the next example, they are actually going to want us to leave it in terms of the constant so that we can use our new function and we can pick any point on the curve and see what the slope is. So instead of going in and using my x to begin with, I am going to leave it alone and not use an x, and I'm going to create a new function that I can plug my x into and find the slope at any point on that function. And so that's what they've done for this one. They want us to find it at 2 points. Well, instead of going through the process twice, I'm going to go through it once. And so I'm going to say, well, I just want to do my definition, f of c plus delta x minus f of c all over delta x. So I want to do this limit here, and then go back and plug those x's in at the end. So plugging in a c plus delta x, I'm going to plug it in here. So I have c plus delta x squared, that's my x squared plus 1, right? Minus just the c plugged in, c squared plus 1. That's just plugging it into the function, right? All over delta x. Now, the biggest problem people have here is just their basic algebra, okay? Foiling, distributing a negative. That's like the biggest problem anyone ever has with these particular questions here. So I do my limit as delta x approaches 0. I'm going to FOIL this guy here. So you end up with c squared plus 2 delta x's. and then plus delta x squared. All right, this whole thing is squared, the delta x. And then distribute your negatives, c squared. Oh, and I keep wanting to leave off my plus 1 at the end. So I'm going to scoot that over so I don't run out of room. And then I have my plus 1 minus, and don't forget to distribute this, I have my c squared minus 1 all over delta x. All right? I can cancel some things here, right? What can I cancel? The 1 can cancel. What else? There we go. So I'm left with this limit problem here. Limit as delta x approaches 0 of 2 delta x plus delta x squared all over delta x. All right? So far, so good. All right, and I need my c here too, by the way. Need my c there. All right, what can cancel?
One of the delta x's.
Yeah, from every single piece. So I end up with limit delta x approaches 0 of 2c plus delta x, right? So plug in a 0. I can plug it in now, right? Didn't I get rid of my problem? So what happens when I plug in a 0 for my delta x? I'm left with just what?
2c.
2c. All right? So this is my new function, and they want me to give the slope at 2 different places. So the slope at the point 0, 1. Well, my c is my x value, so that's going to be 2 times my x value. So my slope there is going to be 0. My slope at -1, 2 is going to be 2 times my c value of -1. So that slope is going to be -2. And so when you create a new function, then anywhere on the curve, you can now tell me the slope without having to do that same process 50 times, right? And so this is the development of the derivative, all right? The slope of the tangent line was the first problem that they came up with and said, oh, we're starting to see a pattern. And so they called that pattern the derivative or the differentiation of that function. And so if you look at page 97, they give you the definition of derivative. Well, it looks an awful lot like the definition of the slope of the tangent line. Except that instead of doing a c there, they're giving you an x, and you are developing a new function, all right? And so slope of the tangent line and derivative are finding the same thing. When you find the derivative, you are finding the slope of the tangent line, all right? When you find the derivative, what you're actually doing is you're finding a function to give you the slope of the tangent line at any point. That's what you are doing. Some of the notation that you want to make sure you know. Notation is very important because your questions may ask you the same thing 50 different ways. Notation for derivatives, all right? It can be the f with the little dash above it, like a prime, all right? So that's first derivative. It can say dy dx, that's the change in y compared to the change in x, all right? It can be just a y prime. Now, these f of x and y mean the same thing, so that's why the y prime. You can see d dx of the function. That means derivative. Or, not as often, but you'll see this capital D with a lowercase x, and I'll do that in yellow, and a lowercase x, which will mean the derivative of y with respect to x. Derivative of y with respect to x. All right? And they tell you that below. You read it like this. The derivative of y with respect to x. Now, the reason it's important to know with respect to x is we will take derivatives with respect to other variables at some point. And so it's important that you know what variable you are taking the derivative with respect to so that you can do the comparison correctly. Some other notation, using limit notation, you'll see down here, you'll see the limit of delta x, delta y over delta x, and then you'll see your derivative definition here, your long definition of it. All right, so then this would say find the derivative. Well, here's the issue with finding the derivative here. Let me show you the long derivative process of finding this derivative. They want me to say f of x plus delta x minus f of x all over delta x, and they want me to find the limit as delta x approaches 0. Well, that's all fine and dandy, except that I'm going to have to do x plus delta x cubed plus 2x plus delta x. If I can write it correctly, that would be great. All right, and that is just my first part of it, right? Minus x cubed plus 2x all over delta x. This process is torture, right? I mean, this is like, really? You want me to cube that binomial? And so what you start finding is you start then finding your shortcuts for derivatives, okay? You start finding your shortcuts.